All right, we are now recording, and while the projector's coming up, let me go over just a couple of announcements, nothing too major. I think I've told you all before about applying to graduate. Certainly if anyone's graduating this term, they should be in already, okay? But I doubt if any of you are graduating this term, but if you are, hopefully your application's in. But if you're graduating next term, then this is the best time to start the process, okay? You can't quite complete everything now, but you can at least start it, which means getting your degree plan, going over that with your advisor, finding out what you have taken, what you're currently taking, and what you need to take in order to graduate. That way, as soon as the spring schedule comes up, and we're working on that now, and that'll probably be, usually they wait until after midterm, when they can finish with all the first mini-term classes, get everybody started in second mini-term, then start messing with the next term. Hopefully that'll be the case this time. We've got a little more time to work on it. But then when you go to register, you can see if you can schedule all those classes you needed. If you can't, okay, then that's a good time to try to get in touch with instructors or department chairs and stuff and try to get your, I hit the button and nothing happened, did it? Let's try it again. I'm not hearing any noise. Are you? Oh, it's on. Okay. Is there something there? I guess it's slowly coming. Let me turn off this for just a moment. Wow. Can y'all read that? Okay, it's getting brighter. Okay. So anyway, to remind you, so if you're not graduating next term, remember the term before you're scheduled to graduate, that's when you should apply, okay? That way you get the opportunity to line everything up. There are no surprises, and hopefully you can get everything done. Now, two other, and I think I've announced these two, but just to remind you, they were looking at, assume still are looking for note takers for, and it may be only on Birmingham, but it may be on either campus. If you are interested in doing that for someone who is unable to take notes themselves, great service to somebody. You get paid to do it. Check with Dr. Renee Herndon here down. Just check at the front desk, and they'll tell you where to go to get to her office. You're really close to it there. They also were looking for tutors, peer tutors in the Space Center. And there's a Space Center on both campuses, and there's also student support services on this campus that hire peer tutors. So if you're interested in doing that, that's even more beneficial because not only are you helping someone else, you're helping yourself know the material better, and you're getting paid. So they pay you for all those. So please consider being a peer tutor. All right. And they were looking for math, biology, computer science, Spanish, and one other I can't remember. But anyway, several subjects. Check them out and see. I think you probably got the email, so check that out. Okay, let's start from the current slide. And this is where we left off last time. We had just finished page 85, and then we're getting ready to start on 86. Any questions on anything we've done so far? All right. Now, just as a reminder, we're getting awfully close to finishing the chapter. I think we'll finish it today. If we do, that means we're ready for the test Thursday? Yay? No? Okay. Well, we can go on and get started in chapter 2 on Thursday, but then Tuesday will need to be the test if you don't feel like you're ready for Thursday. Okay? Now remember this, you also have to have your quiz in before you can take the test, or you have to ask me politely to give you a 0 on the quiz, and I won't want to do it, but if you ask me politely, I have to. Okay, so please get your quizzes in, preferably before the test, so you can get them back and see what you may have missed. And anyone who has turned in a quiz already, you can certainly see it. They're all graded. They're not all the scores on Blackboard yet, but they are graded, and you can see anything you may have missed. So see me right after class and we'll go over that. Okay, I can't return them to you until I get them all in, and I'm missing, looks like, close to a third of them, so please get your quizzes in. All right, any questions? So let's go. Graph of an inverse function. Now tell me something about an inverse function. What do we mean by that? Inverse function. And how would it affect its graph? Remember how we introduced inverse functions? Say again? Someone said something. Sounded good, but I can't hear well. Inverse function. Say again? Okay, that's certainly how we represent it. What does it mean to be an inverse function? Whatever you did with the original function, the inverse function undoes it. Okay? So, if you started with an x here, with the original function, and got a y value, then what does the inverse function do? Start with a y and gives you the x. Very good. Okay? So, what would you expect the graph to look like? Yeah, you've just flipped the coordinates. So that's what we're expecting. Let's see if that's what we get. The graphs of the function f and its inverse function, f inverse, as you were saying, are related in the following way. If the point AB lies on the graph of f, then you know the point BA must be on f inverse. Every point, you interchange the x and the y. That's what it means to be an inverse. And vice versa. Every point BA on the inverse function, that means AB has to be on the original function. That means the graph of f inverse is a reflection of the graph of f in the line y equal x. Does anyone remember what we named this function? Y is equal to f. Y is equal to x. What's the card? My identity card. This is the identity function, okay? This is the identity function. So, it's a reflection across the identity function. Here's your y is equal to f of x, and there's AB. You go over this far on x to get A. You go up this far to get B. Then, on the inverse function, you must go over this far on the horizontal axis, B, and go up this far, A, to get its companion point. And you see that's true for everyone. Any place that it crosses the identity function, the other one will cross there. Now here's another thing to note, and it might seem a little counterintuitive, but if your original function, remember, in order to have an inverse, didn't we talk about this already? Okay. Did we say what kind of function it has to be? A one-to-one function. 1 to 1. Okay? A one-to-one function. And that means it's strictly increasing or strictly decreasing. So here's your f function. It is always increasing. Even here where it slows down, it's always increasing. Well, guess what the inverse is? It's also strictly increasing. Always. And if this was a decreasing function, your inverse function would be always decreasing. Seems like it would be going the other way, but it isn't. Okay? So, well, yeah. It does seem like it should be going this way. Any questions on that? All right. Example 3 then, top of page 86, says sketch the graph. These are fun, aren't they? Of the inverse functions f of x equal 2x minus 3, and f inverse, which is 1/2 of x plus 3, on the same rectangular coordinate system, and show that the graphs are reflections of each other in the line y is equal to f. So let me, y is equal to x. I keep saying f. Okay. Let me get my pen set up. Okay. Now here will be my axes. Okay. We'll do it about here. Now let's just tick off a few points. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4. Ooh, that one's bad. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3. Okay, something like that. Now, how do we graph y is equal to 2x minus 3? Not terribly hard to graph. How would you do that? How would you graph f of x equal 2x minus 3? Pretty easy to do, I hope. Say again? Okay, your y-intercept is negative 3. And by the way, someone else came in while I was yakking before Demetric did. Let me get Demetric before I forget him. Okay, no problem. Okay. And who else? Someone. Okay. Evans, got it. Okay, Chikaya, right? Okay. Anyone else come in? Okay. All right. Now, I heard someone say, start with negative 3, because that's your y-intercept. 0, negative 3. That's right down here. Okay, and where do we go from there? Rise 2, go up 2, right 1, up 2, right 1, up 2, right 1. You get the general idea. It's a linear function going up and down like that. Okay? Now, what color do you want the inverse in? You choose. Red. Okay. I was going to use red for my identity function because the book did. So give me another color. Yellow. Okay, we'll go with yellow. I hope you can see it. Okay, so this will be the yellow function. Now I don't like graphing that one, okay, particularly because, well, it's not too bad. What would be a good point to start with? Give me an x. Okay, 1 would be okay x. I like other x's better. Wait, 1 is a great x. Sorry about that. Yeah, 1's a great x. When x is equal to 1, what is your y, or your f inverse? Say again? 2, okay? So 1, 2. Buckle my... No, I didn't say that, okay. There is the first point. I hope you can see it, okay? Give me another x. Say again? 3, okay? And 3 would give you 3, okay? I see what you're saying now. 3, 3. Somewhere, goodness gracious, it's an ugly graph. Yeah, that's this point right here, and I didn't graph it well the first time. There it is. They're right on top of each other. Give me another one. Negative 1. And what would that give you? Negative 1, 1. That would be right here. Ooh, some of these aren't looking too good because I did space them poorly. Okay, another. Another. Negative 3. And what would that give you? 0. All right. Boy, my spacing is not good. So anyway, here we go. Something like this and going like this. It's got to be a straight line. Obviously, my points weren't lining up too well, but it is supposed to be a straight line, and I didn't even intersect at the place I needed to intersect well. But they're both lines, both linear functions, okay? Need to be if they co-inverse each other. See, this is why I was saving red, because the identity function, you see, they do reflect across that. You see? Both increasing functions, one has a slope of 2. What's the other slope? It's the slope of the inverse function. Help me. Say again? A little louder? 1/2. Excellent. What's this y-intercept? Say again? 2. Not 2. That one. Say again? Not 1. Y-intercept. If you had... Positive 3. Say again? Not 3. You have to multiply this in.
1.5.
1.5, and look at there, almost right on the money, okay? So even my ugly graph came pretty close, okay? So sure enough, it was slope of 1/2, y-intercept of 3/2. That's why I didn't want to start that way, because those would be awful to plot, but we are moving along well. Does that make sense? Do you see that they are reflections across the identity function? Okay? All right, let's move on. Oh, and they list several points. And let's do those two, I guess. Okay? We said this was 0, -3. This was -3, 0. This was 1, -1. This was -1, 1. Should have been right up there. This was 2, 1. This was 1, 2. This was 3, 3. And that was 3, 3. Exactly the same. So you see they do pair up and you reverse the colors every time. Okay? Make sense? That's what makes it an identity function. All right. There is a checkpoint. Please do the checkpoint sometime soon after leaving class. Whenever you got some free time, try to review the checkpoints. So let's see. Oh, yeah. Let's see how they do it. Sorry about that. I forgot they had this one on the slide set. So there it is. Okay. They throw it up there. All right. They listed lots of points. Okay. A few more than we did. Well, one more than we did. They listed -1, -5. For this one, put a -1 in here. You get -2 minus 3 is -5. Put a -5 in here. -5 plus 3 is -2, and half of that would be -1. So sure enough, those two match too. We did the others. Okay, and you could have gone on great. All right. Remind me of your name? Thanks. All right. Gotcha. Okay. Anyone else come in since I called roll? Okay. It appears that the graphs are reflections of each other in the line y is equal to x, the identity function. You can further verify that reflective property testing a few points on each graph, and we just did. All right. Any questions? Excuse me. Okay. Now, note that the following list, and this is what we said before, we've already done these, on the graph of F, if AB is on the graph of F, BA is on F inverse, and we went over every one of those points. Make sense? All right. Any questions? All right. I thought we hadn't gotten to here yet. So let's do example before we move on to one-to-one functions. I thought we had already done that, but let me get back to black here. If I can get the pen to operate. There it goes. All right, example 4. Verify graphically that the functions f of x is equal to x squared. Okay? Now, they have something in parentheses here. X greater than or equal to 0. Wonder why that's there. And g of x, which is the square root of x. Okay? It says verify graphically that they're inverse functions of each other. Okay, now since our x's are going to have to be positive here, I'm going to move my axis over here. And if the x's are positive, in this case, the y's are positive too. Okay? Because you see your f of x is x squared, which is never negative, and your square root of x, the x's are always positive, the y's are always positive. So both of those are in the first quadrant only. So let's tick off a few points here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7. I won't need that many, but we'll put them there. Let's first do, now, I have a question here. Why did we restrict the x's here only to be positive for this x squared? Okay, got to be greater than or equal to 0, and why is that? Because if you allow this to be, x's to be negative, you get here. And that function doesn't have an inverse. We'll talk about it a little bit later. You see, this requires the input to be positive, which of course it would be because that's the output here, and that's always positive. But its output is always positive, meaning this input has to be always positive. Remember, your input and output have to be mirror images of each other, and because this is always positive, the input here has to be positive as well. The output there becomes the input here. So that's why we have to have x greater than or equal to 0. So, give me a few points and we'll plot F. 0, 0. Perfect. Next? 2 what? 2, 4. 1, 2, 3, 4. Somewhere up here. Right. Next? 3, 9. 3, 1, 2, 3, 4. I can't read. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, I'll say it's up here somewhere, okay? We'll put it right there. All right? Can't go any higher there. We left out one we could do. 1, 1. There it is. Okay. Now, that's a parabola which looks something like this. Ooh, half a parabola anyway. How about square root of x? What color you want that? What color? Second? Blue. Light or dark? Light. Okay, we got light blue here. Give me an x. This will be in light blue. 0, 0 will certainly be there. 1, 1 happens also to be there. 4, 2. We go out 4 and up 2. Right? 4 and up 2. Next. 9. That 5, 6, 7, 8, 9, and 3. Somewhere right about here. Okay? So this one is like this. That's half a sleeping parabola. Now, graphically, have we just shown that they reflect across the identity function? Sure looks like it to me. So, yep, those look like they would be inverse functions of each other. One's increasing, the other's increasing. Okay? In fact, let's put it different ways. This one's increasing slowly here, then picks up speed. This one's increasing rapidly here, but then slows down. Exactly inverse of each other. Now do you see why you couldn't have any x's over here in the original function? Couldn't happen. This would be decreasing here, increasing there. They have to be strictly increasing or strictly decreasing. Both of these are increasing. Does that make sense? All right. And you can pick the points. 0, 0 is on both. 1, 1's on both. 2, 4's on that one. 4, 2's on this one. 3, 9's on that one. 9, 3's on this one. Yeah. Well, I should have labeled them, but, you can see them. All right. No questions? Checkpoint bottom of the page. Please do those as soon as you can. So now we're ready for what comes next, which I thought we had already done, but we hadn't. One-to-one functions. Okay, I'm teaching 4 different math classes. I can't remember what I've covered, and this is the only 112, but actually 5 different math classes. Okay. All right. The reflective property of the graphs of inverse functions gives you a geometric test for determining whether a function has an inverse or not. And that test is the horizontal line test. Now, we've had something akin to that. What was that? Vertical line test. That was to show whether it's a function or not. Because with a function, if you have any value x, it can have only one y, so it can only cross the vertical line once, and only once. Now, a regular function could do anything on x's, but to have an inverse, it must be also pass a horizontal line test, meaning it's strictly increasing or strictly decreasing. It can't back up on itself and have an inverse. So that test is called the horizontal line test for inverse functions. A function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. We know that vertical lines have to, now horizontal. Well, why? Okay. Well, let's just imagine that we did have a function that crossed the horizontal line twice. If that had an inverse, then it would be crossing the vertical line twice, and that would be a function. And to be an inverse function, it must be a function. So therefore, if the vertical line test works for any function, horizontal line test has to work for any function with an inverse. Because its inverse would then, if it didn't pass the horizontal line test, the inverse, the main function wouldn't pass the vertical line test. So, good deal. Now, if no horizontal line intersects the graph of f at more than one point, then no y value is matched with more than one x value, what I was just saying. This is a central characteristic of what we call one-to-one functions. Okay? One-to-one function. Only ones that have an inverse. So here's the definition. A function f is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent value. Almost the reverse of what the function, definition of function, when each independent has only one dependent, this now says also every dependent variable corresponds to exactly one value of the independent variable. A function f has an inverse if and only if it is one-to-one. So those go hand in glove. Now what they haven't said, and we'll get to maybe a reason for that later, but here's one. Here's a function that we're looking at earlier. This is the function f of x equals x squared. And that domain is all real numbers, right? So you can pick any number in the world. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Pick a number, you can square it, right? So negative 2 becomes 4, negative 1 becomes 1, 0 becomes 0, 1 becomes 1, 2 becomes 4, 3 becomes 9, and so on. You can do fractions, you can do others, these are the easy ones. Is that a one-to-one function? Everybody see? Okay. No, it isn't, because for any given dependent variable, like this 4, it has an independent variable negative 2, but the same 4 has an independent variable of positive 2, not one-to-one. If you did try to reverse those, and put the y's here and the x's there, then this would be a function, because it fails there, it fails there, it fails lots of places. Okay? It would not be a function. So, that illustrates why it has to be one-to-one to have an inverse. If you're going to flip them and you have more than one y's for a given x, more than one x's for a given y, which is okay for a function, it's not okay for its inverse, because then you flip the two. Does that make sense? All right. Now, the table on the right does not represent a function. That's this one, because for any value of x, you have more than one value of y. Not a function then. Okay? So therefore, so this is just saying the same thing. So f of x equals x squared is not one-to-one and does not have an inverse function unless you restrict its domain. Now, if you take that parabola, and you know how it looks, and you took only the left-hand leg of it, that would be one-to-one. Passes the horizontal line test. That would have an inverse. Or, like we did before, if you took the right-hand wing of it, that is one-to-one. And it does have an inverse, the square root of x. Okay, this one over here would be negative the square root of x, right? Or square root of negative x. Which one is it? Yeah, square root of negative x. Okay, that would work, because all the x's are negative. Okay, so you could take the square root of negative x. So, if you restrict the domain, you can make what looks like it wouldn't have an inverse to have an inverse on that restricted domain only. Okay. How about this one? One-to-one or not? This is example 5. A, bottom of the page. By the way, LarsonPrecalculus.com, interactive version of that type of example, absolutely free website. You don't need a code or anything else to get into it. Just go to that website. You'll see them talk about this. Is that one-to-one? Yes, it is. The only place that looks like it might be a little shady is right in here. It looks like it almost gets flat there, but it never does. Every point here goes up a little bit. Slightly decreasing, increasing, but always increasing. So yes, that is a one-to-one function. So that would have an inverse. Be a little messy to get to it, but we will do that later. Okay? Now, because no horizontal line intersects the graph of f at more than one point, f is a one-to-one function and does have an inverse function. This is not one, I don't think, that you'll do by observation or trial and error. There's another method we're going to get to next. So any questions? All right. Let's look at the B part. Is that a one-to-one function? No. That horizontal line test right there fails. It intersects the function more than once. Now, to make this a one-to-one function, you have to limit the domain. If you limit the domain to just the right-hand side, yeah, one-to-one. Or just the things greater than one. That would be okay. Or if you limit it to only the left-hand side, that is one-to-one. That could have an inverse function, but on a limited domain. And you can do that. It's perfectly permitted in most states. Okay. So, but by itself, just written for all real numbers, nope, not in a one-to-one function. So it does not have an inverse the way it's written. Make sense? All right. Now, and there is a checkpoint bottom of page 87. Now what we've been waiting for, how do we find these inverse functions for any old function? Not just one that's real easy like x plus 3, well, make it x minus 3. Yeah, that'll work, okay? No, something a little more complicated, okay? So for relatively simple functions, like I just said, you can find those by inspection sometimes, okay? For more complicated functions, however, it's best to use the following guidelines. And these are guidelines. I don't like to break them up the same way they do, but we'll talk about that. It says the key step here is their step 3. I number them slightly differently. Interchanging x and y. That's what inverse functions do, right? The x's and y's swap. So that's the key here. That step corresponds to the fact that inverse functions have ordered pairs in which the coordinates are reversed. Okay, so here they are, and I'm going to tell you how I break them down a little bit differently from this, but it's fine. Now, what they do first, and they don't say it, but you almost have to, graph the function, okay? Yeah, okay, yeah, no, we love graphing, right? Or at least think through and convince yourself this is a one-to-one function. So to use a horizontal line test, you almost have to graph it unless you can think through it, okay? So their implied step 0 would be graph the function, then use the horizontal line test to determine whether it has an inverse function. I'll show you in a couple of examples how you can kind of get away from it, okay? Graphing every time. Okay, in the equation for f of x, replace the f of x with what? What is f of x always? Y. Okay, replace f of x with y. We've been doing that, right? Now that you've done that, now you interchange the x and the y. Now I make another line for the next one. Once you've interchanged x and y, since that's the most important step, let's make that a step of its own. Then step 4, solve for y. Okay? They do it in the same step. I say interchange first, then solve for y. Once you solve for y, your new y is now your f inverse. Not f, that was the old y. It's now the f inverse. Now, the next step is the one most of us try to avoid if we can. Verify that f and f inverse are inverse functions of each other. How do we do that? We do f of f inverse, composite, and see if that's equal to x. If it is, fine. And then we're supposed to turn around and do alpha of alpha inverse. And if that is x, even better. Okay, can I get your name, please? Trace. Got it. Thanks. Okay. Anyone else come in since the call draw? Trace, there you are. All right. Good deal. Okay. Most of those are fairly quick to do, except that last one usually takes a little more time. Actually, I would break that down into 2 steps. But anyway. So, let's do it here. Find the inverse function of this. Does anyone remember the first step? Okay, he's jumping right to there, okay? Remember, you first need to graph it. Okay. Now, I'm going to try to avoid graphing it if I can, and let's see if you agree with me on that. What kind of function is that? We had several names of functions. What kind was this one? Help me, anybody. Okay. Let me see if I wrote it slightly differently, would it help? What if I wrote that, and tell me if this is legal, okay? Don't let me do something illegal, okay? Wouldn't that be the same as 5 over 2 minus 3x over 2? Yay or nay? Same thing, right? Okay. Can anyone tell me what kind of function that is? Still not. I think you can, you're just shy, okay? Tell me if this is legal. Let me reverse those two and make it minus 3 halves x plus 5 halves. Can anyone tell? Is that the same thing? Yes, it is. I just reversed the side and pulled out the coefficient and put the x separately. So I did 2 steps at once. Put this in front, this at the end. That's a positive, by the way. And then pulled out the 3 halves and put the x in. That's legal, right? What kind of function is that? You don't answer that one, you're just sitting there, okay? What kind of function is that? Only. What kind is it? Linear. How do you know it's a linear function? You really could tell back here too. What's that? Say again? Yes, it's in the form of mx plus b. You're absolutely right. That is exactly why I wrote it that way. What's more, and this will be true for any linear function, the only allowed value exponent for your independent variable is a 1. And that's here, and here, and here. That's got to be a linear function. There's no x's in the denominator. That would be a negative exponent. And there's no 2's or 3's. There's no 1/2's, no square roots, nothing. The only exponent for the variable is 1. 1 and only 1. That's a linear function. Okay. Now, you told me it's in the form mx plus b. What does this m tell you? Slope. And if it has a slope of negative 3/2, it's going like that, right? And it's a straight line, right? If it's a straight line going like that, can that be anything other than 1 to 1? Every horizontal line only crosses it once. So as soon as you see this is a linear function without a zero slope slope fails, okay? But if it has a slope other than 0, that's a 1 to 1 function. So you don't have to graph that. Now, it would be hard to graph. It would be messy. And I'm lazy, so I don't like messes. Well, I don't mind my writing, but other than that, it's fine. Okay, so this is a 1 to 1 function. See, I just argued my way around not having the graph. Okay, but you could graph it if you want to. Has to pass the horizontal line test. Okay, next step. Okay, we'll go back to this one. What's the next step? After we verified it's 1 to 1. That took way more time than it should have, okay? What's the next step? Replace the f of x with y. Why not? Okay, y is equal to 5 minus 3x over 2. Very good. Now, I think the one that Cody was wanting to jump to right away was, or was that the one you were going to say? Say again? Yeah, swap the x's and y. So what would that become? Say again? X is equal to 5 minus 3y over 2. We just flipped the x's and y's, right? Now the next step. I think someone kept saying this. Okay, yeah, we want to solve for y. Okay? And that's the first step to do so. Now we want to isolate the y. Okay? So first thing you do, multiply both sides by 2. Okay? That wipes out your denominator here. That gives us to be, I'm going to swap sides too if that's okay. Whoa, don't do that. Okay. There we go. All right. So let's do 5 minus 3y is equal to 2x. Okay? Now what? Say again? Yeah, subtract 5 from both sides. And that gives us minus 3y is, because that adds a 0, is equal to 2x minus 5. Okay, good. Now, divide by negative 3. What does that give us? Y is equal to negative 2/3 x. What? You may have said it, I couldn't hear. Plus 5/3. Now, they may have written it 2x minus 5, or, well, they could have written it any way they wanted to. I bet you, if they wanted to make it like the original, that would have been 5 minus 2x over 3. You could have done that. That's a perfectly good answer. No better or no worse than what we did, but now it looks more like the original. Okay? Now, that's not quite done yet. Couple more steps. What are they? Second, replace the y with f inverse. Exactly. That should now your f inverse of x is equal to, let's write it that way, 5 minus 2x over 3. Okay? Now, that kind of looks inverted from what the other one was, but just looking isn't good enough, is it? Okay, even though you may be good looking. Okay, never mind. Okay. But, what do we do for that? Okay? We need to verify. But let's just pause a moment here. Okay? While we're here. Remember, what's the slope here? Negative 3 over 2, meaning it's a decreasing function everywhere. What's the slope here? Negative 2/3. Also decreasing everywhere. Remember I said if that function was decreasing, the inverse must be decreasing. If the function is increasing, its inverse must be increasing. At different rates for sure, but it must be decreasing. Okay. So that was just another verification. And they're both lines. That's good. So what we need to do is prove they're inverses of each other. Okay? Now, I sure hope I haven't made a mistake. Have y'all been following this? Have we made all the steps right? Okay? You know, here is the bizarre thing, and it just gripes me no end. This one isn't in the book. Okay. Now, I uploaded the current PowerPoint, and I thought that would take care of this problem. It doesn't, okay? The one in the book is a very different problem from this one. Sorry about that. Let's go on and finish this one, then we'll come back and do the one in the book. It's even a little bit harder, but it's good to do. So let's take these. And I'm just going to write the f inverse up here. F inverse of x is equal to 5 minus 2x over 3. Okay? Okay. Now I'm going to erase everything else. I don't know what I should have done. I was going to erase everything, but that would erase this. Okay, so let's get rid of this. Okay. Now what we're going to do now is, again, an exercise in composition of functions, because we're going to compose these two together and see if indeed they're inverses of each other. And really you need to do this every time. It's sort of like checking your answer. I always like to check my answer to make sure I didn't make a stupid mistake. So this is checking the answer. It's just a really difficult. So how do we verify that they're inverses? Okay, we could graph it, but they actually say do the number 5, verify their inverses by showing that, okay, well, the domain and the range were perfectly equal to that because everything was all real numbers. And that f of f inverse is x and f inverse of f is x. So here's what we've got to do. F of f inverse. We've got to show what that is. How do we do it? This is the exercise in doing composite functions again. What do we do first? Put the inside first. So it's f of, and what was our f inverse? 5 minus 2x over 3. Now we're operating on that new entity with the function f. And what does the function f tell us to do? Where do we start? 5 minus 3. And then whatever's inside the parentheses, that's what goes next, right? So that would be, yuck. Okay. That would be 5 minus 2x over 3, right? And the whole thing is divided by 2, right? F function is what restriction we have here. What you're doing is operating with F on F inverse, okay? So what you do, you start with the 5 here, minus 3 times what's inside the parentheses, which is this thing, 5 minus 2x over 3, and then do your big division line divided by 2. You see that? That's how you do composites, okay? Now, what would be your first step in simplifying that? The 3 over 3 is 1, so that disappears. So that gives me 5 minus, keep it in parentheses, 5 minus 2x all over 2. I don't like those parentheses there, so I'm going to take them off. What would that be? 5 minus 5 plus 2x over 2. And what's 5 minus 5? 0. And what's 2x over 2? X. There we have it. We showed the f of f inverse was indeed x. But we're also supposed to show that f inverse of f of x. We got to do that one too. So how do I proceed here? F inverse of, what's your f of x? 5 minus 3x over 2. And what does f inverse start with? A 5 minus 2. But here instead of x, you put what's inside the parentheses, which is 5 minus 3x over 2. And this is divided by 3. Okay? And you'll see the 2's go out. They've been dating. Yet the 5's go out. And you're left with minus a minus, which is plus 3x over 3 is x. Yeah, I did it real fast that time, didn't I? Tegan made me do it. She was moving me along there. Okay. Take your time on that. Do you see what happened? Okay. I did it really fast. But sure enough, the same thing happened. All those things disappeared, and you wind up with x again. And that's exactly what you want. Very seldom will composites of each other equal the same thing. With inverse functions, they must, and that same thing must be x. Okay. Now let's go back and do the books number 6. I'm so sorry. I thought when I loaded when I used to use the CD or the DVD that came with the book, it had the old one. I said, well, I'm going to pull it off the internet and use the current one. They still have the old one on there. I wasn't paying attention. So can I go on and erase this? This next one's, it's just a little bit more complicated, but it is a little more complicated. Okay? So let's do it. Find the inverse function of f of x, where f of x is 5 minus x, 5 minus x over 3x plus 2. Yeah, y'all let me just go on and on and on. You didn't even tell me it wasn't the same 6 in the book. Okay? I should have picked up on that. What's our first step? Second? Okay. He likes to skip this one too. Yeah, okay? Graph it. Oh, no, you don't mean that, do you? This one's far worse to graph. I can't talk my way out of this one. Okay? I'm going to have to graph it. Okay? But I'm going to give you a few hints on how you can graph these a little bit more easily. Okay? Whew. Well, I wish we would have skipped this one. Skip this one. All right. Now, first place. What's problematic about that function? What? What's problematic about it? It has the variable in the denominator. Now, anytime you have a variable in the denominator, what have you got to worry about? Yes, you can't divide by 0. So basically, you got to say the denominator, 3x plus 2, cannot equal what? 0. Okay, now we have to solve that inequality. Let's solve it. What will we do first? Say again? Subtract 2 from both sides, and that would give us 3x cannot equal negative 2. And then divide by 3, and that tells us that x cannot equal negative 2/3. Oh, what a beautiful number. So, if x can't be negative 2/3, let me tick off a few points here. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Somewhere up there. 1, 2, 3, 4, 5, 6, 7. Somewhere up there. Okay, something like that. So negative 2/3 is right over here somewhere. So I'm going to get my red pen and do a vertical line up there, because that line represents x equal 2/3, right? And it can't ever be there. So the red line says don't touch it, don't cross it, don't ever go there. You can get close to it, but you can't touch it. Okay? So there is what we call a vertical asymptote. All right. Now, I'm going to do something else here to this problem. This is jumping ahead. You're going to do this in section 2.6. So, but they gave you the problem here, so I feel like I have to show you how to do it. Okay? I would write that numerator as minus x plus 5 over 3x plus 2. That's the same function, right? But I'm just putting it in descending orders of power. Okay, now what I'm going to do next, and this is something you haven't done yet, but this is the horizontal asymptote. Well, the horizontal asymptote is where the function goes in the long run for large values of x. And what we look at then is the ratio of the leading terms, and that's why I wrote it in this way, so it's easy to see. What's the ratio of those leading terms? Ratio of leading terms. Say again? Negative 1 over 3, is that what you said? Yes, negative 1/3. That becomes your horizontal asymptote. Boy, they've got such nice little problems here. So in the same red ink, which I already changed, I shouldn't have, I'm going to do negative 1/3, which is somewhere like there. I'm going to do a horizontal asymptote there. Now, you're not supposed to know that yet, so just pretend you don't, but this is what we got. Now, in a sense, that becomes your new axis, okay? Not really, but it sort of does. You'll see why in a minute. Now, let me tell you about horizontal asymptotes. The function can touch it, it can cross it, but in the long run, it's long Lewis. No, in the long run, you're going to be approaching that. Okay? So that's what we're going to get to later. Now, let's go back to a couple of other things. Okay? Let me get my pen back to black. Another thing I'm interested in is x-intercepts. What is an x-intercept? Anyone tell me? What is an x-intercept? What's true about an x-intercept? Okay, what does it mean? Nick Saban would be upset if he didn't know this. It's where the x-axis intercepts the function, right? In other words, if that function tries to cross the x-axis, that's where it's going to cross it. So what's true about everything on the x-axis? Think of it as ordered pairs. Everything on the x-axis has something in common. Y is 0. So what we do, and where's your y in this problem? I don't see a y here. Oh, that's your f of x. Okay, now how can f of x be 0? Only if that numerator is 0. 0 over something is going to be 0. It doesn't matter what the denominator is. If that numerator is 0, the function is 0, right? So what value of x is going to make the y 0? 5. So x equals 5, y is equal 0. That's your y-intercept. Okay? Your x-intercept. 5, 0. 1, 2, 3, 4, 5, 0. Right there it is, right? And this is Ryan, right? I just got to find you. I know you're in here somewhere. Yeah, Ryan Edwards, right? Okay, good deal. All right, so we got 1 point, the x-intercept. Give me another point that's of interest. The x-intercept's of interest, then the y-intercept would be of interest too. How do we get the y-intercept? Say again? I can't hear you. How do you get the y-intercept? How did you get the x-intercept? Set y equals 0. How do you get the y-intercept? Set x equals 0, because everywhere the x is 0 is on the y-axis. Okay? And that's where it's going to intercept. So when x is equal to 0, what do we have here? Anybody? X equals 0. X equals 0. 5 halves. 2.5. Okay? I love this setup. Okay. All right. So that would be at 2.5. 1, 2.5. There's your x-intercept. Guess what? We can plot half of the function right here. Here's how we do it. You know from here, as it approaches your y-intercept, your vertical asymptote, it gets closer and closer and closer, but can never get there. It's not supposed to have any wobbles in it. But as it approaches your horizontal intercept, horizontal asymptote, it gets closer and closer. It may touch that one, but this one doesn't. So there's half the function right there. Okay? Now, I'll give you a hint. The other half of the function can't be down here. Why not? It wouldn't be a function. Okay? So it's either over here or over there. And it either mirrors like this or it mirrors like that. Okay? So that we need to find out. So let's pick a point. Some point, say, -1. That is going to tell us whether we're up here or down there. So what happens if we put a -1 in here for x? You get what? Positive 6 over, which would be -6. So at -1, you're way down there at -6. I know where it lives now. Okay? It's down here. At -1, you're down here 1, 2, 3, 4. Somewhere way down here at -6. Okay? Well, I know where it's heading here, closer and closer to that vertical asymptote. And I know where it has to go here, closer and closer to the horizontal asymptote. Okay? And you notice no more x-intercepts, you can't. Okay? No more y-intercepts, you can't. We're stuck in that quadrant. And there, sure enough, is our function. Now, what do we notice about it? Why did we graph it in the first place? To see if it's... Say again? Yeah, to see if it's 1-to-1. And that's going to tell you whether it has inverse. Is this a 1-to-1 function? Yes. Even out here where it gets very flat, it never is totally flat. It's approaching that horizontal asymptote, same thing over there, but never touching it. Just gets closer and closer and closer, but never is perfectly flat. So it does have a 1-to-1. It is a 1-to-1 function. It does have an intercept. And notice it's strictly decreasing here and strictly decreasing there. It's just discontinuous there. Okay. And there are the twain to meet. Okay. Now, so we've done the first step. That was all for the first step. That's why I didn't want to do this problem. Okay. Now, what's the next step? Not yet. Oh, yes, yeah. Okay, yeah. You're saying it right. You replace f of x with y. So that becomes y is equal to 5 minus x over 3x plus 2. Perfect. Now what? This is the important step. Yeah, interchange the x's and y's. So what does that become now? X equal 5 minus y over 3y plus 2. Okay. Now what do we have to do? Solve for y. What's the problematic y here? And the denominator. So I like to get it out of the denominator. How could we do that? Multiply both sides by 3y plus 2. Okay? So this will be multiplied by 3y plus 2. Everybody see that? Okay? So that's going to wipe out this side. And that gives us, can you multiply those two? I know it looks ugly. 3xy plus 2x is equal to 5 minus y. Now what's the goal here? Get y by itself. Isolate the y. So what? Okay, we get all the y's on one side and all the x's on the other, and terms with no y's on the other. So subtract 2x from both sides and add y to both sides. Is that what you said? Okay. Here that goes to 0, these go to 0, and you have 3xy plus y is equal to 5 minus 2x. Got it? Now what? Factor out a y. Perfect. So you can isolate it. Y times 3x plus 1 is equal to 5 minus 2x. And now what? Divide both sides by 3x plus 1, 3x plus 1, and that gives us, I'm going to skip a step if I can here, f inverse, which is your y. That's the step I'm skipping because I just don't want to write anymore. 5 minus 2x over 3x plus 1. Now, can you look at that and say, oh yeah, that has to be the inverse? No, I can't. You know, they look somewhat similar, but there's enough differences that I don't know. I got to check. Okay? And that is, of course, what we do next. I don't have room for it, so I'm going to, if you'll remind me what that is. Someone's written it down, right? The f inverse? Okay. I'm going to erase everything else. Everything. And, remember what the function was, okay? Not this. It was what? 5 minus x over, yeah, no, but this is f. I forgot. I erased that too. 3x plus 2. And our f inverse was 5 minus 2x over, second? 3x plus 1. Okay. And what's that last step? The check it step? Verify. Okay. People. Yuck! All right. Maybe this comes at a perfect time. Don't math teachers like to say this, or the math books like to say it? The rest is left to the student. Okay. This next step is a harder one, which is not the harder one. It's just consuming. You do f of f inverse. Okay, and then you do f inverse of f. And that's left to the student. We've run out of time. Sorry about that. So please do that. This one's a little bit hairier. Please do it. Check and make sure that these are inverses of each other. So, does it look like the test may be, yeah, we're almost through, but not quite. We'll finish on Thursday. The test will be next Tuesday, right? Okay, homework exercises here. Any of the odds, 7 through 13, they're all at Calc Chat, 9's at Calc View. Either 15 or 17, they're both at Calc Chat, 15's at Calc View. Do 19, it's at Calc Chat. Do any of the odds, 21 through 31, they're all at Calc Chat, 23's at Calc View. Do 33, it's a Calc Chat. Do 35, it's a Calc Chat. Either 37 or 39 or both, they're at Calc Chat. 41 or 43, they're both at Calc Chat, 41's at Calc View. Do any of the odds 45 to 53, they're all at Calc Chat, 45's at Calc View, thank you. Okay, and then do any of the odds 55 to 69, they're all at Calc Chat, 61's at Calc View. We will come back and finish the rest of those next time. Good deal. Thank you so much. Okay, sure. Anyone that wants to see your quiz, you certainly may. Let me go on and shut this down so I don't say anything